What if everything in the universe is secretly connected in ways we can't see or touch? This isn't science fiction, it's the bizarre reality of quantum entanglement, a phenomenon so strange that even Albert Einstein called it spooky action at a distance. Imagine two particles separated by vast distances, instantly influencing each other's behavior as if they were still linked. It's a concept that defies everything we thought we knew about space and time, forcing us to rethink the very fabric of reality. Today, we're diving into this mind-bending mystery to explore how quantum entanglement is rewriting the rules of physics, challenging our understanding of the cosmos, and paving the way for revolutionary breakthroughs in technology and communication. From the smallest particles to the vast expanse of the universe, this is a journey into the unknown, a story that might just change the way you see everything. So, let's unravel the secrets of quantum entanglement together and discover how it's reshaping our understanding of existence itself. At the heart of quantum entanglement lies a concept so strange that it feels like it belongs in a science fiction novel. Picture this: two particles, perhaps electrons or photons, become so deeply connected that they share a kind of cosmic bond. No matter how far apart they are, whether they're in the same room or on opposite sides of the galaxy, their properties are mysteriously linked. If you measure one particle and find it spinning clockwise, the other will instantly spin counterclockwise, as if they're communicating faster than the speed of light. It's like having a pair of dice that always land on the same number, no matter where or when you roll them. This isn't just a quirky coincidence, it's a fundamental property of the quantum world. To understand how this works, we need to dive into the idea of superposition. In the quantum realm, particles don't have definite states until they're observed. Instead, they exist in a kind of fuzzy, undefined state, a combination of all possible outcomes. Imagine flipping a coin, but until you look at it, it's neither heads nor tails, it's both at the same time. When two particles become entangled, their superpositions are intertwined, creating a shared state that defies classical logic. It's as if the particles are dancing in perfect harmony, their fates forever linked. But how do we know this isn't just a theoretical curiosity? Enter the groundbreaking experiments that changed everything. In the 1930s, Albert Einstein, along with physicists Boris Podolsky and Nathan Rosen, proposed the EPR paradox, a thought experiment designed to challenge the idea of quantum entanglement. They argued that if entanglement were real, it would require spooky action at a distance, something they believed was impossible. Decades later, physicist John Bell developed a theorem that put this idea to the test. Bell's theorem showed mathematically that if entanglement were real, certain correlations between particles would violate the rules of classical physics. And when scientists finally conducted experiments based on Bell's ideas, the results were undeniable. Entanglement is real, and it's as strange as it sounds. This discovery didn't just shake the foundations of physics, it opened the door to a world where particles can communicate instantaneously across vast distances, defying the limits of space and time. But here's the kicker: this phenomenon isn't just a quirk of nature. It's a clue that our understanding of reality might be incomplete. As we delve deeper into quantum entanglement, we're forced to confront questions that challenge everything we thought we knew. What does it mean for two particles to be connected in such a profound way? And what does this tell us about the true nature of the universe? The answers might just rewrite the story of space and time as we know it. Einstein's theory of relativity transformed our understanding of the universe, painting a picture of space and time as a single, dynamic fabric. It tells us that nothing can travel faster than the speed of light, a cosmic speed limit that keeps the universe orderly and predictable. But then there's quantum entanglement, a phenomenon that seems to laugh in the face of such rules. Here, particles can influence each other instantaneously, no matter how far apart they are. It's as if the universe has a hidden backdoor, allowing connections that bypass the usual constraints of space and time. This clash between relativity and quantum mechanics isn't just a minor disagreement, it's a fundamental conflict that has puzzled scientists for decades. Einstein himself was deeply troubled by quantum entanglement. To him, the idea that particles could communicate faster than light seemed impossible, even absurd. He famously called it spooky action at a distance, a phrase that captured his unease with the concept. For Einstein, the universe was governed by strict, local rules. Nothing could influence anything else without some form of physical connection. But quantum entanglement suggested something far stranger, a universe where particles could be intimately linked, even if they were light years apart. It was a challenge to everything relativity stood for, and it sparked one of the most intense debates in the history of science. At the heart of this debate is a question that still lingers today. How can two frameworks, both brilliantly successful in their own domains, be so incompatible? Relativity excels at explaining the behavior of stars, galaxies, and the large-scale structure of the cosmos. Quantum mechanics, on the other hand, is the key to understanding the bizarre behavior of particles at the smallest scales. Yet when it comes to entanglement, these two theories seem to be speaking entirely different languages. Relativity says nothing can outpace light. Quantum mechanics suggests that entanglement defies that limit entirely. It's a paradox that has driven physicists to rethink the very foundations of reality. Over the years, countless experiments have sought to resolve this tension. Researchers have tested entanglement over increasing distances, from a few meters to hundreds of kilometers, and the results have been consistent. Entangled particles do indeed influence each other instantaneously. These findings have only deepened the mystery, pushing scientists to explore new ideas that might bridge the gap between relativity and quantum mechanics. Concepts like quantum gravity, string theory, and even the holographic principle have emerged as potential solutions, each offering a fresh perspective on how the universe might work at its deepest level. What's fascinating is that this clash isn't just a theoretical puzzle, it's a driving force behind some of the most exciting advancements in modern physics. The tension between relativity and quantum mechanics has inspired groundbreaking experiments, innovative technologies, and entirely new ways of thinking about the cosmos. And as we continue to explore these ideas, we're inching closer to a deeper understanding of reality, one that might finally reconcile these two great pillars of physics. The story of quantum entanglement isn't just about rewriting the rules, it's about discovering a new language to describe the universe itself. But here's where things get truly exciting. Quantum entanglement isn't just a fascinating quirk of nature, it's the backbone of one of the most transformative technologies of our time, quantum computing. Unlike classical computers, which rely on bits that can be either 0 or 1, quantum computers use qubits, which can exist in a superposition of both states simultaneously. And when these qubits become entangled, they unlock a whole new level of computational power. Imagine a machine that can explore countless possibilities at once, solving problems in seconds that would take classical computers millennia. This isn't just an upgrade, it's a revolution. Take Google's quantum supremacy experiment, for example. In 2019, their quantum processor, Sycamore, performed a calculation in just 200 seconds that would have taken the world's most powerful supercomputer 10,000 years. How? By harnessing the power of entangled qubits. These qubits, linked through entanglement, allowed the processor to explore multiple solutions simultaneously, achieving a level of efficiency that's simply impossible for classical systems. It was a watershed moment, proving that quantum computing isn't just theoretical, it's here, and it's changing the game. So, what makes entanglement so powerful in this context? In a classical computer, each bit operates independently, processing information in a linear, step-by-step fashion. But in a quantum computer, entangled qubits work together in a coordinated dance, sharing information instantaneously across vast distances. This means they can tackle problems that involve enormous complexity, like simulating molecular interactions for drug discovery or optimizing large-scale systems like traffic networks or financial markets. The possibilities are staggering. One of the most promising applications of quantum computing lies in cryptography. Classical encryption methods rely on the difficulty of factoring large numbers, a task that's incredibly time-consuming for traditional computers. But a quantum computer with its entangled qubits could crack these codes in a fraction of the time. This has profound implications for cybersecurity, forcing us to rethink how we protect sensitive information in the digital age. At the same time, quantum computing also offers new ways to create unbreakable encryption, using the principles of entanglement to secure data in ways that classical systems never could. And it doesn't stop there. Imagine a future where quantum computers revolutionize medicine by simulating complex biological processes, leading to breakthroughs in treatments for diseases like cancer or Alzheimer's. Or consider their potential in artificial intelligence, where they could process vast datasets and uncover patterns that are invisible to classical algorithms. Fields that once seemed stuck in theoretical limbo could leap forward thanks to the power of entanglement, but with great power comes great responsibility. As quantum computing advances, it raises important questions about how we'll use this technology and what safeguards we'll need to put in place. Will it be a force for good, solving some of humanity's greatest challenges, or could it disrupt industries, economies, and even global security? The answers aren't clear yet, but one thing is certain. Quantum entanglement is no longer just a curiosity of physics, it's a cornerstone of the future. And as we continue to unlock its potential, we're not just reshaping technology, we're redefining what's possible. What if space itself is an illusion, a kind of cosmic mirage that emerges from something far more fundamental? This is the radical idea that quantum entanglement is forcing us to consider. For centuries, we've thought of space as the stage on which the universe plays out, a fixed backdrop where stars, planets, and particles interact. But entanglement suggests something far stranger, that space might not be fundamental at all. Instead, it could be an emergent property, something that arises from the intricate web of connections between particles. It's like realizing that the stage isn't real, it's just a projection of the actor's movements. To grasp this idea, let's think about a hologram. When you look at a holographic image, it appears three-dimensional, full of depth and texture. But the information that creates that image is actually stored on a flat, two-dimensional surface. In a similar way, some physicists propose that the three-dimensional space we experience might emerge from a deeper, more fundamental layer of reality, one governed by entangled particles. In this view, space isn't a fixed, pre-existing thing. It's more like a dynamic network of relationships constantly being woven together by the connections between particles. This concept, known as spacetime entanglement, has profound implications for our understanding of the universe. If space emerges from entanglement, then the very fabric of reality might be stitched together by these quantum connections. It's as if the universe is a vast, interconnected tapestry, with each thread representing an entangled pair of particles. And just as a tapestry can change depending on how the threads are woven, the structure of space itself could shift and evolve based on the patterns of entanglement. But how does this work in practice? One clue comes from the study of black holes. According to some theories, the information about everything that falls into a black hole isn't lost, it's encoded on the event horizon, the boundary that marks the point of no return. This idea, known as the holographic principle, suggests that the three-dimensional space inside the black hole is somehow projected from the two-dimensional surface of the event horizon. It's a striking parallel to the idea that space itself might emerge from a deeper, entangled reality. This line of thinking doesn't just challenge our understanding of space, it also hints at a deeper unity in the laws of physics. If space and time are emergent properties of entanglement, then the divide between quantum mechanics and general relativity might not be as insurmountable as it seems. In fact, some physicists believe that space-time entanglement could be the key to a unified theory of everything, one that reconciles the quantum world with the cosmic scale. It's a tantalizing possibility, suggesting that the universe's deepest secrets might lie not in the stars or the particles, but in the invisible threads that connect them. Of course, this is still a work in progress. The idea that space emerges from entanglement is both thrilling and speculative, a frontier of physics that's still being explored. But the fact that we're even asking these questions shows how far we've come. Quantum entanglement, once dismissed as a bizarre quirk, is now at the heart of some of the most profound ideas in science. It's not just rewriting the story of space and time, it's inviting us to imagine a universe that's far more interconnected, dynamic, and mysterious than we ever dreamed. And as we continue to unravel these mysteries, we might just find that the true nature of reality is more extraordinary than we ever imagined. If space can be redefined by quantum entanglement, what about time? This is where things take an even stranger turn. While entanglement has already shown us that particles can influence each other instantaneously across vast distances, what if this influence isn't bound by the flow of time as we know it? Imagine two particles entangled not just across space, but across time itself. It's a concept that turns our everyday understanding of cause and effect on its head, suggesting that the past, present, and future might be far more intertwined than we ever realized. Welcome to the mind-bending world of quantum time. In the quantum realm, time doesn't always behave the way we expect. Take, for example, a thought experiment that extends the famous Schrödinger's cat paradox. In the classic version, a cat in a box is both alive and dead until someone observes it. But what if the act of observation isn't just tied to the present moment? What if the outcome of that observation could somehow influence events that have already happened? This isn't just speculation, it's a real possibility in the quantum world. Experiments have shown that entangled particles can exhibit correlations that seem to defy the arrow of time, creating a kind of feedback loop where the future appears to influence the past. One of the most striking examples comes from a series of experiments known as delayed choice experiments. In these setups, scientists create scenarios where the decision to measure a particle's properties is made after the particle has already passed through an experimental setup. Remarkably, the results suggest that the particle's behavior can change retroactively, as if it knows what measurement will be made in the future. It's as though time itself is flexible, bending to accommodate the entangled connections between particles. These findings challenge the very notion of causality, the idea that cause must always precede effect. This leads us to a profound question. What if entanglement isn't just a bridge across space, but a bridge across time? If entangled particles can influence each other across vast distances, why couldn't they do the same across different moments in time? Some physicists have even proposed that entanglement could create a kind of quantum network, linking events in the past, present, and future into a single, interconnected web. In this view, time might not be a straight line, but more like a tapestry, with threads weaving together moments that are separated by years, centuries, or even millennia. But how does this fit into our everyday experience of time? After all, we live in a world where yesterday feels firmly in the past and tomorrow is still ahead. The key lies in the scale. At the level of everyday objects, the effects of quantum entanglement and its strange relationship with time are so subtle that they're almost impossible to detect. But zoom into the level of particles and the rules change entirely. Here, time becomes fluid and the boundaries between past, present, and future blur. It's a reminder that the universe operates on multiple layers, each with its own set of rules. So, what does this mean for our understanding of time? If entanglement can create connections that transcend the usual flow of cause and effect, then the past might not be as fixed as we think. The future could hold a kind of influence over the present, and the present might ripple backward into the past. It's a dizzying idea, one that forces us to rethink not just the nature of time, but our place within it. Are we bound by the linear progression of moments, or are we part of a larger, more intricate dance, where every action is connected to every other, no matter when or where it occurs? As we grapple with these questions, we're reminded that the universe is far stranger and more interconnected than we ever imagined. Quantum entanglement isn't just rewriting the story of space and time, it's inviting us to see reality in a whole new light. And as we continue to explore these ideas, we might just discover that the past, present, and future are not separate chapters, but threads in a single, timeless tapestry. The implications are as vast as the cosmos itself, and the journey to understand them is only just beginning. Black holes have long been the ultimate cosmic enigmas, regions of space where gravity is so intense that not even light can escape. But what if these mysterious objects hold the key to understanding quantum entanglement on a cosmic scale? It turns out, black holes and entanglement are deeply intertwined in ways that could solve one of the most perplexing puzzles in physics, the black hole information paradox. To see how, let's take a closer look at what happens when a black hole meets the quantum world. When matter falls into a black hole, it doesn't just vanish. According to Stephen Hawking's groundbreaking work in the 1970s, black holes slowly evaporate over time, emitting a faint glow of particles known as Hawking radiation. This radiation carries away energy, causing the black hole to shrink and eventually disappear. But here's the catch: if the black hole vanishes, what happens to all the information about the matter that fell into it? According to quantum mechanics, information can never be truly lost, it must be conserved. Yet, black holes seem to defy this rule, creating what's known as the information paradox. This is where quantum entanglement enters the picture. Imagine the particles of Hawking radiation aren't just random emissions, but are deeply entangled with the black hole itself. In this scenario, the information about the matter that fell into the black hole isn't lost, it's encoded in the entangled particles of the radiation. It's like a cosmic jigsaw puzzle where the pieces are scattered across the universe, but the connections between them preserve the full picture. Quantum entanglement becomes the glue that holds the puzzle together, ensuring that no information is ever truly destroyed. But how does this work in practice? Think of the black hole as a vault and the entangled particles as the keys. As the black hole emits Hawking radiation, each particle carries a tiny fragment of the information stored inside. These particles are entangled with the black hole, meaning their properties are linked in a way that preserves the overall information. Even as the black hole evaporates, the information remains intact, spread across the entangled particles. It's a delicate dance where the quantum connections ensure that nothing is lost, even as the black hole itself fades away. This idea has profound implications for our understanding of black holes and the universe itself. If entanglement can preserve information in the face of a black hole's immense gravitational pull, it suggests that the fabric of reality is far more resilient than we thought. It also hints at a deeper connection between quantum mechanics and gravity, two forces that have long seemed incompatible. Could entanglement be the missing link that unites these two pillars of physics? Some physicists believe it might be, pointing to the holographic principle as a potential solution. The holographic principle proposes that all the information contained within a volume of space can be represented as a hologram on its boundary. In the case of a black hole, this means the information inside could be encoded on its event horizon, the boundary that marks the point of no return. Entanglement could be the mechanism that allows this encoding, creating a bridge between the quantum world and the cosmic scale. It's a radical idea, but one that's gaining traction as researchers explore the connections between entanglement, black holes, and the nature of spacetime. What's truly exciting is that this isn't just theoretical speculation, it's a hypothesis that's being tested. Scientists are using advanced simulations and experiments to probe the relationship between entanglement and black holes, searching for evidence that could confirm these ideas. If they succeed, it could revolutionize our understanding of the universe, revealing how the smallest particles and the largest structures are connected in ways we're only beginning to grasp. So, what does this mean for the story of space and time? If entanglement can solve the black hole information paradox, it could unlock the secrets of the universe's most mysterious objects, from the birth of black holes to the fate of the cosmos itself. It's a reminder that the universe is far more interconnected than we ever imagined, with quantum entanglement weaving a web that ties everything together. And as we continue to explore these ideas, we're not just solving a cosmic puzzle, we're uncovering the hidden threads that bind the fabric of reality. What if our entire universe is like a hologram, a three-dimensional projection of information encoded on a two-dimensional surface? This is the mind-bending idea behind the holographic principle, a theory that's reshaping how we think about space, time, and the very nature of reality. At its core, the holographic principle suggests that everything we see, touch, and experience might emerge from a deeper, more fundamental layer of information, one that's intricately woven together by quantum entanglement. It's as if the universe is a cosmic cinema, and entanglement is the projector turning a flat, two-dimensional screen into the rich, three-dimensional world we inhabit. The roots of this idea trace back to the study of black holes, those enigmatic regions of space where gravity is so intense that nothing can escape. When matter falls into a black hole, it doesn't just disappear. Instead, according to physicist Stephen Hawking, black holes emit a faint glow of particles known as Hawking radiation. But here's the puzzle. If the black hole eventually evaporates, what happens to all the information about the matter that fell into it? Quantum mechanics insists that information can never be truly lost, but black holes seem to defy this rule. This conundrum, known as the black hole information paradox, led scientists to a startling realization. Perhaps the information isn't lost at all. It's encoded on the black hole's event horizon, the boundary that marks the point of no return. This insight gave rise to the holographic principle, which proposes that all the information contained within a volume of space can be represented as a hologram on its boundary. Think of it like a three-dimensional movie projected from a flat, two-dimensional screen. The screen holds all the data needed to create the illusion of depth, even though it's fundamentally flat. In the same way, the holographic principle suggests that the three-dimensional universe we experience might be a projection from a two-dimensional surface, with entanglement acting as the mechanism that stitches it all together. But how does entanglement fit into this picture? Imagine two particles separated by vast distances, yet still connected in a way that defies classical physics. Their properties are intertwined, as if they share a hidden bond that transcends space and time. Now, scale this idea up to the universe itself. If entanglement can link particles across vast distances, could it also be the glue that holds the holographic universe together? Some physicists believe the answer is yes. entanglement might be the invisible thread that weaves the fabric of reality, connecting the two-dimensional boundary to the three-dimensional world we perceive. This idea has profound implications for our understanding of the cosmos. If the universe is a hologram, then space and time might not be fundamental at all. They could be emergent properties arising from the intricate web of entangled information. It's a radical shift in perspective, one that challenges everything we thought we knew about the nature of reality. And it's not just a theoretical curiosity. It's a hypothesis that's being tested through advanced experiments and simulations as scientists search for evidence that could confirm the holographic principle. What's truly fascinating is how this idea bridges the gap between quantum mechanics and gravity, two forces that have long seemed incompatible. Quantum mechanics governs the behavior of particles at the smallest scales, while gravity shapes the large-scale structure of the cosmos. The holographic principle suggests that entanglement could be the missing link, providing a framework where these two realms can coexist. It's a tantalizing possibility, one that could lead us toward a unified theory of everything, a single set of rules that explains the universe from the smallest particles to the largest galaxies. So, what does this mean for our perception of reality? If the universe is a hologram, then the world we experience might be just the surface of something far more profound. The boundaries between space and time, matter and energy, past and future could blur, revealing a deeper, interconnected reality that's governed by the quantum dance of entanglement. It's a vision of the cosmos that's as awe-inspiring as it is humbling, reminding us that the true nature of existence might be far stranger and more beautiful than we ever imagined. And as we continue to explore these ideas, we're not just rewriting the story of space and time, we're uncovering the hidden threads that weave the tapestry of reality itself. What if every decision you've ever made, every path you've taken exists simultaneously in parallel universes? This isn't just the stuff of science fiction. It's a serious scientific idea rooted in quantum mechanics. And at the heart of this mind-bending concept lies quantum entanglement. Could entangled particles be the invisible threads that connect not just points in space but entire universes? Let's dive into the idea of the multiverse and explore how entanglement might be the key to unlocking infinite realities. The concept of the multiverse suggests that our universe isn't the only one. It's just one of countless others, each with its own unique history and set of physical laws. One of the most compelling frameworks for this idea is the many worlds interpretation of quantum mechanics. According to this theory, every time a quantum event occurs, like a particle being measured, the universe splits into multiple branches, each representing a different outcome. It's like standing at a crossroads where every possible turn you could take happens, creating an infinite tree of branching realities. And here's where entanglement comes in. These parallel universes might not be entirely separate. Instead, they could be subtly connected through the entangled states of particles, forming a vast, interconnected web of possibilities. Imagine a tree with countless branches, each one representing a different universe. Now picture entangled particles as the sap flowing through those branches, linking them in ways that defy our everyday understanding of reality. In one universe, a particle might spin clockwise. In another, it spins counterclockwise. But because they're entangled, these particles share a connection that transcends the boundaries of their individual universes. It's as if the multiverse isn't just a collection of isolated worlds. It's a single, unified structure stitched together by the quantum threads of entanglement. But how does this idea hold up under scrutiny? The many worlds interpretation has been a topic of intense debate since it was first proposed in the 1950s. Critics argue that it's untestable as we can't observe these parallel universes directly. However, supporters point to the strange behavior of entangled particles as evidence that something extraordinary is happening behind the scenes. If particles can influence each other instantaneously across vast distances, why couldn't they also be connected across different realities? It's a tantalizing possibility, one that challenges us to rethink not just the nature of the universe, but the very fabric of existence itself. This idea also raises profound questions about free will and destiny. If every possible outcome of every quantum event exists in some parallel universe, does that mean our choices are predetermined? Or do we have the power to shape our own path across the multiverse? While the answers remain elusive, the concept of entanglement offers a fascinating perspective. Even if there are infinite universes, they might all be part of a larger, interconnected whole, where every choice and every possibility is woven together in a cosmic tapestry. So, what does this mean for our understanding of reality? If entanglement truly connects parallel universes, it could revolutionize not just physics, but philosophy, cosmology, and even our sense of identity. It suggests that the boundaries between here and there, now and then, might be far more fluid than we ever imagined. And as we continue to explore these ideas, we're not just uncovering the secrets of the multiverse, we're discovering that the true nature of existence might be more interconnected, dynamic, and infinite than we ever dreamed. The journey into the multiverse is just beginning, and entanglement might be the map that guides us through the unknown. What if the mysteries of the human mind are deeply connected to the strange world of quantum physics? For centuries, consciousness has been one of the most elusive puzzles in science. How does the physical brain give rise to thoughts, feelings, and self-awareness? Now, some researchers are suggesting that the answer might lie in the bizarre phenomenon of quantum entanglement. Could the same process that links particles across vast distances also be at work inside our brains, weaving the fabric of our thoughts and perceptions? This idea might sound like science fiction, but it's rooted in serious scientific exploration. One of the most prominent theories comes from physicist Roger Penrose and anesthesiologist Stuart Hameroff. Together, they've proposed that consciousness isn't just a product of classical brain activity. It might emerge from quantum processes happening at the tiniest scales within our neurons. At the heart of their theory is the idea that microtubules, tiny protein structures inside neurons, could act as quantum processors, using entanglement to create the rich, interconnected experience we call consciousness. Imagine your brain as a symphony orchestra with each neuron playing its part. In a classical view, the music is created by the individual instruments working in harmony. But in a quantum view, the orchestra is also connected by invisible threads of entanglement, allowing the musicians to play in perfect unison, even when they're not directly interacting. This quantum coherence, Penrose and Hameroff argue, could be the key to understanding how the brain generates the seamless flow of thoughts, memories, and emotions that make up our inner world. But how could something as fragile as quantum entanglement survive in the warm, noisy environment of the brain? Critics have long argued that quantum effects are too delicate to play a role in something as complex as consciousness. Yet, recent research suggests that nature might have found a way to protect these quantum processes. Some studies have shown that certain biological systems, like photosynthesis in plants, rely on quantum coherence to achieve near-perfect efficiency. If nature can harness quantum effects in such delicate systems, why not in the brain? The implications of this idea are staggering. If consciousness arises from quantum processes, it could fundamentally change how we understand the relationship between mind and matter. Instead of seeing the brain as a purely classical machine, we might need to view it as a quantum system, where entangled particles create the intricate web of thoughts and perceptions that define our experience. This could even bridge the gap between the physical and the mental, offering a new way to explore age-old questions about the nature of self, free will, and the very essence of being. Of course, this theory is still highly speculative, and the scientific community is far from reaching a consensus. But the fact that researchers are even considering such ideas shows how quantum entanglement is pushing the boundaries of our understanding, not just in physics, but in fields as diverse as neuroscience and philosophy. It's a reminder that the universe is full of surprises, and that the answers to some of our deepest questions might lie in the strange, interconnected world of quantum mechanics. So, where does this leave us? If entanglement truly plays a role in consciousness, it could open up entirely new avenues for exploring the mind, from developing novel treatments for neurological disorders to creating artificial systems that mimic human thought. It's a bold vision, one that challenges us to rethink not just the brain, but the very nature of reality itself. And as we continue to explore these ideas, we might just discover that the threads of quantum entanglement don't just connect particles across space, they might also weave the tapestry of our inner lives. What if the flow of time, the steady march from past to future, isn't just a fundamental fact of the universe, but something that emerges from the strange world of quantum entanglement? This is the bold idea that's reshaping how we think about the arrow of time, the one-way direction that seems to govern our lives. We're used to thinking of time as a straight line, moving inexorably forward, but entanglement suggests that the story might be far more intricate. It's as if time isn't just a river flowing in one direction, it's a river with a hidden current powered by the quantum connections between particles. To understand how entanglement might shape the arrow of time, let's start with a simple question. Why does time move forward at all? In the macroscopic world, we see events unfold in a clear sequence. Cause always comes before effect. A glass shatters because it was dropped, not the other way around. But in the quantum realm, things aren't so straightforward. Entangled particles seem to defy the usual rules of cause and effect, creating correlations that don't depend on the order in which they're observed. It's as if the past, present, and future are all part of a single, interconnected web, with entanglement weaving the threads together. This idea becomes even more fascinating when we consider the concept of entropy, the measure of disorder in a system. According to the second law of thermodynamics, entropy always increases over time, which is why we see things like ice melting or eggs breaking. They move from order to disorder. But what if entanglement plays a role in this process? Some physicists suggest that the correlations created by entangled particles could be the driving force behind the increase in entropy, effectively giving the arrow of time its direction. It's like the current in a river guiding everything downstream. Without entanglement, the river might flow in any direction or not at all. Imagine two entangled particles separated by vast distances. When one particle is measured, its state instantly influences the other, creating a correlation that seems to transcend time. Now, scale this idea up to the entire universe. If entanglement links particles across space and time, it could create a network of correlations that define the flow of time itself. The past isn't just a fixed set of events, it's a tapestry of entangled connections, constantly influencing the present and future. And just as a river's current shapes the landscape it flows through, entanglement could be shaping the very structure of time. But here's where things get truly mind-bending. If entanglement defines the arrow of time, could it also give us clues about how time might behave in extreme conditions, like near a black hole or during the birth of the universe? Some theories suggest that in these extreme environments, the usual flow of time could break down, creating regions where the past, present, and future blur together. Entanglement might be the key to understanding these phenomena, offering a new way to explore the mysteries of time itself. This isn't just a theoretical curiosity, it's a potential solution to one of physics' greatest puzzles. For decades, scientists have struggled to explain why time moves in one direction. even though the fundamental laws of physics seem to work equally well in reverse. Entanglement could be the missing piece of the puzzle, bridging the gap between the microscopic world of quantum mechanics and the macroscopic world we experience every day. It's a reminder that the universe is far more interconnected than we ever imagined, with the threads of entanglement weaving together the fabric of reality itself. So, what does this mean for our understanding of time? If entanglement truly shapes the arrow of time, it could revolutionize not just physics, but our sense of how the universe works. It suggests that time isn't just a passive backdrop, it's an active participant, shaped by the quantum connections that bind everything together. And as we continue to explore these ideas, we might just uncover the hidden currents that guide the flow of time, revealing a universe that's more dynamic, interconnected, and mysterious than we ever dreamed. The journey to understand time is far from over, but with entanglement as our guide, we're one step closer to unraveling its deepest secrets. What if the invisible threads of quantum entanglement are woven into the very fabric of the cosmos, shaping the universe in ways we're only beginning to understand? This idea takes on a whole new dimension when we consider dark matter, the mysterious substance that makes up more than 80% of the universe's mass. Dark matter doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. Yet its gravitational pull is so powerful that it holds galaxies together, sculpting the large-scale structure of the universe. But what if dark matter isn't just a passive player in this cosmic drama? What if it's deeply connected to the quantum world through entanglement, forming a hidden web that binds the cosmos together? Picture the universe as a vast spider's web stretching across billions of light years. The strands of this cosmic web are made of dark matter, invisible but undeniably present, guiding the formation of galaxies and galaxy clusters. Now imagine that each strand of this web isn't just a gravitational thread, it's a network of entangled particles, linked in ways that transcend space and time. Just as a spider's web vibrates when touched, the cosmic web might hum with the subtle interactions of entangled dark matter particles, creating a hidden symphony that shapes the universe. This isn't just a poetic analogy, it's a serious scientific idea. Some physicists have proposed that dark matter particles could be entangled, forming a quantum network that underlies the visible structure of the cosmos. In this view, the cosmic web isn't just a product of gravity, it's also a manifestation of quantum entanglement, with dark matter particles acting as the invisible threads that stitch the universe together. It's a radical concept, but one that could explain some of the deepest mysteries of the cosmos, from the distribution of galaxies to the nature of dark matter itself. But how could entanglement play a role in something as massive as dark matter? At first glance, quantum effects seem too delicate to influence the large-scale structure of the universe. Yet, recent research suggests that entanglement might not be confined to the microscopic world. In fact, it could scale up to cosmic proportions, shaping the behavior of dark matter particles on a galactic scale. These entangled particles might form a kind of quantum scaffolding, creating the intricate patterns we observe in the distribution of galaxies. It's as if the universe has a hidden blueprint, one that's written in the language of entanglement. This idea also opens up new possibilities for understanding dark matter. If dark matter particles are entangled, their interactions could be far more complex than we've imagined. Instead of being simple, inert objects, they might exhibit collective behaviors, forming quantum networks that ripple through space and time. These networks could explain why dark matter clumps together in certain ways, creating the cosmic web that astronomers have mapped across the universe. It's a tantalizing possibility, one that could bridge the gap between the quantum realm and the cosmic scale. So, what does this mean for our understanding of the universe? If entanglement is indeed linked to dark matter, it could reveal a hidden layer of reality, one that's been invisible to us until now. The cosmic web might not just be a structure, it could be a living, dynamic network shaped by the quantum connections between dark matter particles. And as we continue to explore these ideas, we're not just uncovering the secrets of dark matter, we're discovering that the universe is far more interconnected, intricate, and mysterious than we ever imagined. This journey into the quantum depths of dark matter isn't just about solving a cosmic puzzle, it's about redefining our place in the universe. If entanglement truly shapes the cosmic web, it suggests that the universe is more than just a collection of stars and galaxies. It's a vast, interconnected system where the smallest particles and the largest structures are bound together by invisible threads. And as we peel back the layers of this cosmic mystery, we might just find that the true nature of reality is far more extraordinary than we ever dreamed. What if the seeds of the universe were planted by the strange, invisible connections of quantum entanglement? To explore this idea, we need to travel back in time, way back to the very beginning of everything, the Big Bang. This explosive event, which set the stage for the cosmos as we know it, is often described as a moment of unimaginable energy and density. But what if entanglement was there, quietly weaving the first threads of the universe's structure? Let's dive into how this quantum phenomenon might have played a starring role in the birth of the cosmos. In the first moments after the Big Bang, the universe was a seething cauldron of energy and particles, all packed into an unimaginably tiny space. Within this chaotic soup, quantum fluctuations, tiny, random variations in energy, rippled through the fabric of reality. These fluctuations might seem insignificant, but they were anything but. In fact, they could have been the spark that ignited the universe's expansion, setting off a chain reaction that would shape everything we see today. And here's where entanglement comes in. These quantum fluctuations didn't just happen in isolation. They were deeply interconnected, with entangled particles influencing each other across the newborn cosmos. Imagine the early universe as a canvas and quantum entanglement as the brush that painted the first strokes. As the universe expanded, these entangled connections stretched and evolved, creating a network of correlations that would eventually give rise to the galaxies, stars, and cosmic web we observe today. It's as if the universe's structure was encoded in these quantum threads, with entanglement acting as the blueprint for everything that followed. This idea isn't just poetic, it's a serious scientific hypothesis, one that could explain why the universe looks the way it does. One of the most striking pieces of evidence for this idea comes from the cosmic microwave background, the faint afterglow of the Big Bang. This ancient light, which fills the entire universe, carries tiny temperature variations that scientists believe were caused by quantum fluctuations in the early cosmos. These variations aren't random, they form intricate patterns like fingerprints left behind by the primordial universe, and some researchers believe that these patterns might bear the signature of entanglement, a hidden code that reveals how the universe's structure emerged from the quantum realm. But how exactly could entanglement have shaped the universe? One possibility is that it created a kind of cosmic harmony, linking particles in a way that amplified certain quantum fluctuations while smoothing out others. These amplified fluctuations would have grown over time, becoming the seeds for galaxies and galaxy clusters. Meanwhile, the smoother regions would have evolved into the vast voids we see in the cosmic web. It's a delicate balance, one that entanglement might have orchestrated in the universe's earliest moments. This idea also sheds new light on the concept of inflation, the rapid expansion of the universe that occurred just after the Big Bang. Some theories suggest that entanglement could have driven this expansion, acting as a kind of quantum fuel that powered the universe's growth. If true, entanglement wouldn't just be a passive observer in the cosmic drama, it would be the engine that set the whole story in motion. It's a bold vision, one that reimagines the Big Bang not as a single explosive event, but as a quantum symphony with entanglement conducting the music of creation. So, what does this mean for our understanding of the universe? If entanglement played a role in the Big Bang, it could rewrite the story of our cosmic origins, revealing a universe that's more interconnected and dynamic than we ever imagined. The galaxies, stars, and planets we see today might all trace their roots back to the quantum connections forged in the first moments of existence. It's a humbling thought, one that reminds us how deeply we're connected to the cosmos, not just as observers, but as part of its unfolding story. As we continue to explore these ideas, we're not just uncovering the secrets of the universe's birth, we're discovering that the true nature of reality might be far stranger and more beautiful than we ever dreamed. And with every new insight, we're reminded that the story of the cosmos is still being written, with entanglement as one of its most mysterious and powerful characters. The journey to understand our origins is far from over, but with each step, we're getting closer to unraveling the deepest mysteries of existence. What if the bizarre connections of quantum entanglement could create shortcuts across the universe? This idea might sound like science fiction, but it's a serious scientific possibility, one that could redefine how we think about space, time, and even the potential for interstellar travel. At the heart of this concept lies a fascinating connection between entanglement and wormholes, those theoretical tunnels through spacetime that have long captured the imagination of scientists and storytellers alike. Could entangled particles be the key to unlocking these cosmic shortcuts? Let's dive into this mind-bending idea and explore how the quantum realm might hold the secrets to traversing the universe. To understand how entanglement and wormholes might be linked, let's start with the basics of wormholes. Picture a sheet of paper with two dots drawn far apart. If you fold the paper so the dots overlap, you can poke a hole through both layers, creating a shortcut between them. In the same way, a wormhole is a theoretical tunnel that connects two distant points in spacetime, effectively folding the universe to bridge the gap. The catch: wormholes are incredibly unstable and require exotic forms of matter to stay open, something we've never observed in nature. But here's where entanglement comes in. Some physicists believe that the strange, instantaneous connections between entangled particles could mimic the behavior of a wormhole, creating a kind of quantum bridge across spacetime. Imagine two entangled particles as the ends of a wormhole. Even though they're separated by vast distances, their properties are mysteriously linked, as if there's an invisible tunnel connecting them. This idea, known as the ER=EPR conjecture, suggests that entanglement and wormholes might be two sides of the same coin. In this view, every pair of entangled particles could be thought of as a tiny wormhole, with the entanglement acting as the thread that ties them together. It's like having a cosmic subway system where entangled particles serve as the stations and the tunnels are the wormholes that connect them. But how does this work in practice? Let's say you have two entangled particles, one on Earth and another on a distant planet. According to the ER=EPR conjecture, the instant connection between these particles isn't just a strange quirk of quantum mechanics, it's a physical link, a microscopic wormhole that bridges the vast expanse of space. While we can't use these tiny wormholes to send people or objects yet, they offer a tantalizing glimpse into how the universe might be stitched together at its most fundamental level. It's a radical idea, but one that's gaining traction as researchers explore the deep connections between quantum mechanics and spacetime. This concept could revolutionize our understanding of space travel. If entanglement truly creates wormhole-like connections, it might one day be possible to harness these quantum bridges to traverse the cosmos. Imagine a future where spacecraft don't need to travel through vast stretches of space. They could simply enter a wormhole connected by entangled particles, emerging light years away in an instant. It's a vision that sounds like it's straight out of a sci-fi novel, but it's rooted in the cutting-edge science of today. Of course, there are still huge challenges to overcome. Wormholes, whether quantum or classical, are incredibly fragile and require enormous amounts of energy to stabilize. And while entanglement offers a potential pathway, we're still a long way from understanding how to scale it up for practical use. But the mere possibility that entanglement and wormholes could be connected opens up a world of exciting possibilities, from unlocking the secrets of spacetime to redefining the limits of exploration. So, what does this mean for the future of space travel? If entanglement can create shortcuts across the universe, it could transform our ability to explore the cosmos, making distant stars and galaxies far more accessible. It's a reminder that the universe is full of surprises, and that the answers to some of our deepest questions might lie in the strange, interconnected world of quantum mechanics. As we continue to explore these ideas, we're not just uncovering the secrets of entanglement, we're discovering a new way to navigate the cosmos, one that could take us to places we've only dreamed of. The journey is just beginning, and the possibilities are as vast as the universe itself. What if the speed of light, the ultimate cosmic speed limit, isn't as absolute as we once thought? For over a century, Einstein's theory of relativity has stood as the cornerstone of modern physics, teaching us that nothing can travel faster than light. It's a rule that governs everything from the motion of stars to the behavior of particles. But quantum entanglement throws a fascinating wrench into this idea, suggesting that particles can influence each other instantaneously, no matter how far apart they are. It's as if the universe has a secret communication channel that bypasses the speed of light entirely. How can this be, and what does it mean for our understanding of the cosmos? To grasp how entanglement challenges the speed of light, let's revisit what Einstein's theory tells us. According to relativity, the speed of light, about 300,000 kilometers per second, is the maximum speed at which anything can travel. This limit ensures that cause and effect remain orderly. Nothing can influence anything else faster than light can bridge the distance between them. It's a rule that keeps the universe predictable and consistent. But entangled particles seem to defy this rule. When you measure one particle, its entangled partner instantly responds, as if they're sharing information faster than light could possibly travel between them. It's like two people on opposite sides of the world flipping a coin and always getting the same result, no matter how far apart they are. This apparent violation of relativity has sparked intense debate among physicists. If entanglement allows particles to communicate instantaneously, does that mean information is traveling faster than light? The answer isn't as straightforward as it might seem. While entangled particles do exhibit correlations that seem to defy the speed of light, these correlations don't involve the transfer of information in the traditional sense. Instead, they reflect a deeper, more mysterious connection, one that doesn't rely on signals moving through space. It's as if the particles are part of a single, unified system, where their properties are intertwined in ways that transcend distance. One of the most famous experiments to explore this idea is the Bell test, which has been conducted in various forms since the 1960s. In these experiments, scientists measure the properties of entangled particles separated by large distances. The results consistently show that the particle states are correlated in ways that can't be explained by any local classical theory. Instead, they align perfectly, as if they're communicating instantaneously. These findings have been confirmed repeatedly, leaving physicists with a profound question. How can the universe allow such seemingly faster-than-light connections without breaking the rules of relativity? The key lies in understanding what's actually happening during entanglement. While the particle states are correlated, no usable information is being transmitted faster than light. You can't use entanglement to send a message or communicate across vast distances in an instant. Instead, entanglement reveals a deeper layer of reality, where particles are connected in ways that don't depend on space and time as we know them. It's a subtle but crucial distinction, one that keeps entanglement from outright violating relativity, even as it challenges our understanding of the universe's fundamental rules. So, how are physicists working to reconcile these seemingly conflicting ideas? One approach is to explore the idea of non-locality, the concept that particles can be connected in ways that don't rely on physical proximity. In this view, entanglement isn't about faster-than-light communication. It's about a fundamental interconnectedness that exists beyond the constraints of space and time. Another possibility is that entanglement reveals a flaw in our current understanding of spacetime, hinting at a deeper, more unified theory that could reconcile quantum mechanics and relativity. These ideas aren't just theoretical curiosities, they could revolutionize our understanding of the universe. If entanglement truly transcends the speed of light, it might open the door to new ways of thinking about space, time, and the very fabric of reality. It's a reminder that the universe is far stranger and more interconnected than we ever imagined, and that the rules we take for granted might just be the tip of the cosmic iceberg. As we continue to explore these mysteries, we're not just challenging the limits of science, we're redefining what's possible. And who knows, the answers we uncover might just rewrite the story of the universe itself. Picture a world where your most sensitive information, bank details, medical records, even government secrets, could be transmitted with absolute security, impervious to hackers or eavesdroppers. Now imagine that same system allowing data to travel instantly, as if distance no longer mattered. This isn't a distant sci-fi dream. It's the promise of a quantum internet, a revolutionary network powered by the strange and powerful phenomenon of quantum entanglement. At its core, this new kind of internet relies on entangled particles to create connections that are not only faster, but also fundamentally secure in ways that classical systems could never achieve. But how does it work, and why is it such a game changer? The key to the quantum internet lies in the unique properties of entangled particles. When two particles become entangled, their states are linked in such a way that measuring one instantly determines the state of the other, no matter how far apart they are. This instantaneous connection could be harnessed to create a new kind of communication network, where information is encoded in the quantum states of particles and transmitted without the risk of interception. Imagine sending a message that's encrypted in such a way that any attempt to intercept it would immediately alter the quantum state, rendering the data useless to the intruder. This level of security isn't just an improvement, it's a paradigm shift, offering a level of protection that's theoretically unbreakable. One of the most exciting real-world examples of this technology in action is China's quantum satellite, MISHUS. Launched in 2016, MISHUS is the first satellite designed to test quantum communication on a global scale. Using entangled photons, the satellite has successfully demonstrated quantum key distribution, a method of securely sharing encryption keys over vast distances. In one groundbreaking experiment, MISHUS sent entangled photons to ground stations over 1,200 kilometers apart, creating a secure communication link between them. This achievement marked a major milestone in the development of a quantum internet, proving that such a network is not just possible but already within reach. But the quantum internet isn't just about security, it's also about speed. In a classical internet, data travels as electrical signals or light pulses through cables, limited by the speed of light and the physical infrastructure of the network. A quantum internet, on the other hand, could leverage entanglement to enable instantaneous data transfer, bypassing the delays imposed by distance. It's like having a direct line between 2 points where information doesn't need to travel through the physical space in between. This could revolutionize fields like finance, where milliseconds matter, or enable real-time collaboration across the globe without the lag of traditional networks. Of course, building a quantum internet isn't without its challenges. Entangled particles are incredibly delicate, and maintaining their fragile states over long distances requires cutting-edge technology and precise control. Researchers are working on developing quantum repeaters, devices that can extend the range of entanglement by amplifying and relaying quantum signals. These repeaters would act like the routers of the quantum internet, ensuring that entangled connections can span the globe. While the technology is still in its early stages, the progress so far is incredibly promising, with teams around the world racing to bring the quantum internet to life. The implications of a quantum internet go far beyond faster and more secure communication. It could transform entire industries from healthcare to defense by enabling new ways of sharing and processing information. Imagine a future where quantum networks allow scientists to collaborate on global challenges like climate change or disease research in real time, or where businesses can operate with unprecedented levels of security and efficiency. The quantum internet isn't just a technological leap, it's a cultural and societal one, redefining how we connect, communicate, and collaborate. As we stand on the brink of this new era, it's clear that the quantum internet holds the potential to reshape our world in ways we're only beginning to understand. From the groundbreaking experiments of today to the transformative technologies of tomorrow, the journey to a quantum-connected future is just beginning. And with each step forward, we're not just building a new kind of network, we're unlocking a new way of thinking about the very nature of connection itself. The quantum internet isn't just a tool for the future, it's a glimpse into a world where the boundaries of space, time, and security are redefined by the invisible threads of entanglement. What if the universe isn't a collection of separate objects but a single, interconnected whole? This is the profound question that quantum entanglement forces us to ask. At its core, entanglement suggests that the boundaries we see between objects, between you and me, between Earth and distant stars, might be illusions. Instead, the universe could be more like a cosmic tapestry, where every thread is intricately woven into the fabric of reality. Each particle, no matter how far apart, is connected to every other, creating a web of relationships that defies our everyday understanding of space and time. It's a vision of the cosmos that doesn't just challenge physics, it reshapes how we see ourselves and our place in the universe. Think of reality as a vast, interconnected network, where every particle is a node in an invisible web. When two particles become entangled, they're not just linked by chance, they're part of a deeper unity, a shared existence that transcends distance. This idea isn't just a scientific curiosity, it's a philosophical revelation. If entanglement is real, then the universe isn't a collection of isolated parts, it's a single, unified system where every action ripples through the whole. It's as if the universe is constantly whispering to itself, maintaining a hidden dialogue that we're only just beginning to hear. This interconnectedness has profound implications for how we understand reality. In the classical view, the world is made up of separate objects, each existing independently of the others. But entanglement suggests that this view might be incomplete. Instead, the universe could be more like a symphony where every note is connected to every other, creating a harmony that's greater than the sum of its parts. In this view, the boundaries between objects, between you and the screen, between Earth and the stars, are more fluid than we think. They're not hard lines, but points of connection in a vast, dynamic network. This idea also challenges our sense of individuality. If everything is connected at the quantum level, then the distinction between self and other might be more about perspective than reality. It's like looking at a tapestry up close. You see individual threads, but step back and the threads blend into a single image. In the same way, entanglement suggests that we're not isolated beings, but part of a larger, interconnected whole. It's a humbling thought, one that invites us to rethink not just the universe, but our place within it. But what does this mean for our understanding of reality? If the universe is fundamentally interconnected, then the way we perceive the world might be just one layer of a much deeper truth. The solid, separate objects we see around us could be illusions, projections of a reality that's far more intricate and unified than we ever imagined. It's like realizing that the stage of a play isn't real, it's just a backdrop for the actor's movements. In the same way, space and time might be the stage, while entanglement is the hidden script that guides the performance. This idea isn't just philosophical, it's practical too. If the universe is a tapestry of entangled connections, then understanding these connections could unlock new ways of thinking about everything from technology to human relationships. Imagine a future where we harness entanglement to create systems that are more efficient, more secure, and more in tune with the natural world. It's a vision that's not just about advancing science, but about deepening our connection to the cosmos. So, as we explore the mysteries of entanglement, we're not just uncovering the secrets of the universe, we're discovering a new way of seeing ourselves. The cosmic tapestry isn't just a metaphor. It's a reminder that we're all part of something greater, a universe that's more interconnected, more dynamic, and more beautiful than we ever imagined. And as we continue to unravel its threads, we might just find that the true nature of reality is far stranger and more profound than we ever dreamed. The journey is just beginning, and the possibilities are as vast as the cosmos itself. What if the key to finding extraterrestrial life lies not in radio signals or telescopes, but in the strange, invisible threads of quantum entanglement? As we continue our exploration of the cosmos, scientists are beginning to consider how this bizarre phenomenon might revolutionize the search for alien intelligence. Imagine a communication system so advanced that it bypasses the limitations of distance and time, allowing civilizations separated by light years to share information instantaneously. Quantum entanglement could be the foundation of such a system, a cosmic telephone line that connects worlds across the universe. To understand how entanglement might play a role in interstellar communication, let's revisit its core principles. When two particles become entangled, their properties are linked in such a way that measuring one instantly determines the state of the other, no matter how far apart they are. This instantaneous connection defies our everyday understanding of space and time, offering a potential way to transmit information without the delays imposed by the speed of light. For a civilization advanced enough to harness this phenomenon, entanglement could serve as the ultimate communication tool, enabling real-time conversations across the vast expanse of the cosmos. Think of entanglement as a cosmic telephone line, where each entangled particle pair acts as a direct connection between 2 points. On one end, a message is encoded in the quantum state of a particle. On the other end, the entangled partner instantly reflects that change, effectively transmitting the information. Unlike traditional radio signals, which degrade over distance and take years or even centuries to travel between stars, an entanglement-based system would operate instantaneously, making it an ideal method for interstellar communication. It's a technology that sounds like it's straight out of science fiction, but it's rooted in the very real physics of the quantum world. But how could we detect such a system if it exists? One possibility is that advanced extraterrestrial civilizations might use entanglement to send signals that are undetectable by conventional means. These signals wouldn't travel through space as electromagnetic waves. Instead, they would exist as correlations between entangled particles, invisible to our current technology. Detecting them would require entirely new methods, perhaps involving quantum sensors or networks designed to pick up on these subtle, non-local connections. It's a challenge that pushes the boundaries of our scientific imagination, but it's also an exciting opportunity to rethink how we search for extraterrestrial life. This idea also raises intriguing questions about the nature of advanced civilizations. If entanglement-based communication is possible, it suggests that such societies have mastered not only quantum mechanics, but also the ability to manipulate particles on a cosmic scale. They might have developed technologies that allow them to create and maintain entangled pairs across vast distances, or even engineer entire quantum networks spanning galaxies. Detecting these networks could provide the first concrete evidence of intelligent life beyond Earth, offering a glimpse into civilizations far more advanced than our own. Of course, this is still speculative, and there are significant hurdles to overcome. Entangled particles are incredibly delicate, and maintaining their connections over interstellar distances would require extraordinary precision and control. But the fact that we're even considering these possibilities shows how quantum entanglement is reshaping our approach to the search for extraterrestrial life. It's a reminder that the universe is full of surprises, and that the answers to some of our deepest questions might lie in the most unexpected places. So, what does this mean for our quest to discover alien intelligence? If entanglement can indeed serve as a cosmic telephone line, it could bring us closer than ever to making contact with civilizations beyond our own. By expanding our search beyond traditional methods and embracing the strange, interconnected world of quantum mechanics, we might just unlock the secrets of the cosmos. The journey to find extraterrestrial life is far from over, but with entanglement as our guide, we're exploring new frontiers and opening doors to possibilities that once seemed unimaginable. The universe is vast, mysterious, and full of potential, and the next great discovery could be just a quantum connection away. What if the next great leap in physics is already unfolding right before our eyes? Quantum entanglement, once dismissed as a bizarre quirk of the quantum world, is now at the forefront of scientific exploration, driving some of the most exciting and transformative research in modern physics. From unraveling the mysteries of spacetime to redefining the limits of technology, entanglement is shaping the future of our understanding in ways that were unimaginable just a few decades ago. As scientists dig deeper into this phenomenon, they're not just answering old questions, they're uncovering entirely new ones, paving the way for discoveries that could revolutionize our view of the cosmos. One of the most promising areas of research is the quest to unify quantum mechanics and general relativity, two of the most successful theories in physics, and yet completely incompatible. Quantum mechanics governs the behavior of particles at the smallest scales, while general relativity describes the large-scale structure of the universe. For decades, physicists have struggled to reconcile these two frameworks, but entanglement might hold the key. Theories like quantum gravity and the holographic principle are exploring how entangled particles could bridge the gap, offering a unified description of reality that works at all scales. It's a bold vision, one that could finally solve one of physics' greatest puzzles. In laboratories around the world, groundbreaking experiments are pushing the boundaries of what we know about entanglement. Researchers are testing entanglement over increasingly vast distances, from Earth to satellites in orbit, to see if these connections hold over cosmic scales. Others are probing the limits of entanglement in extreme environments, like the intense gravitational fields near black holes or the high-energy conditions of particle colliders. Each experiment brings us closer to understanding how entanglement operates in the real universe and how it might shape the fundamental laws of physics. But entanglement isn't just a tool for theoretical exploration, it's also driving practical advancements that could transform technology as we know it. Quantum computers, which rely on entangled qubits to perform calculations at unimaginable speeds, are already demonstrating their potential to solve problems that classical computers can't touch. Quantum networks built on the principles of entanglement promise to create a new era of secure communication, with applications ranging from cybersecurity to financial systems. Even fields like medicine and artificial intelligence are beginning to explore how entanglement could unlock new possibilities, from simulating complex biological processes to accelerating the development of advanced algorithms. Perhaps the most exciting aspect of entanglement is the way it challenges us to think differently about the universe. Instead of seeing space and time as fixed, independent entities, entanglement suggests that they might emerge from deeper, more fundamental connections. This shift in perspective could lead to entirely new ways of understanding reality, from the birth of the universe to the nature of consciousness itself. It's a reminder that the cosmos is far stranger and more interconnected than we ever imagined, and that the answers to our deepest questions might lie in the most unexpected places. As we stand on the brink of this new era in physics, one thing is clear: entanglement isn't just a curiosity, it's a gateway to a future filled with possibilities. From rewriting the rules of spacetime to unlocking the secrets of the quantum world, its potential is limitless, and as scientists continue to explore its mysteries, we're not just uncovering the secrets of the universe, we're shaping the future of science itself. The journey is just beginning, and the discoveries waiting to be made could change everything we thought we knew about reality. The story of entanglement is far from over, and the next chapter might just be the most thrilling yet. What if the mysteries of quantum entanglement aren't just scientific puzzles, but a reflection of the limits of human understanding? At its core, entanglement challenges everything we think we know about reality: our intuition, our sense of space and time, even our ability to comprehend the universe at its most fundamental level. It's as if nature is presenting us with a cosmic puzzle, one that might never be fully solved, yet endlessly inspires us to keep searching. This isn't just a question for physicists, it's a philosophical journey that forces us to confront the boundaries of what we can know. Consider how entanglement defies our everyday experience. In the world we see and touch, objects are separate, distinct, and bound by the rules of cause and effect. But in the quantum realm, particles are deeply interconnected, their fates tied together in ways that seem to ignore distance and time. It's as if the universe is whispering a secret that we're only beginning to hear, a secret that doesn't fit neatly into the frameworks we've built to understand it. This disconnect between quantum behavior and our classical intuition is more than just a scientific challenge. It's a humbling reminder of how much we still have to learn. Imagine trying to solve a puzzle where the pieces keep changing shape. Every time you think you've figured out how quantum entanglement works, it reveals another layer of complexity. Take, for example, the famous Bell tests, which have repeatedly confirmed that entangled particles behave in ways that defy classical explanations. These experiments don't just deepen the mystery, they force us to question whether our current tools and concepts are even capable of fully describing the quantum world. It's like trying to read a book written in a language we don't yet understand, with symbols that shift and change as we stare at them. This isn't just a challenge for science, it's a profound philosophical question. If nature operates in ways that our minds struggle to grasp, does that mean there are limits to human knowledge? Or does it simply mean we need to develop new ways of thinking, new frameworks that go beyond our classical intuition? Some physicists, like David Bohm, have proposed alternative interpretations of quantum mechanics, suggesting that entanglement might be part of a deeper, hidden order that we're only beginning to glimpse. Others, like Niels Bohr, argue that the quantum world is inherently uncertain, and that our role as observers is fundamentally intertwined with the reality we measure. The beauty of entanglement lies not just in its strangeness, but in the questions it raises about the nature of reality itself. It's a reminder that the universe is far more complex and mysterious than our current understanding can capture. And while that might seem frustrating, it's also incredibly inspiring. After all, science thrives on mystery. It's the unknown that drives us to explore, to experiment, and to imagine new possibilities. Quantum entanglement isn't just a puzzle to solve. It's a gateway to a deeper appreciation of the cosmos and our place within it. For future generations of scientists, entanglement represents both a challenge and an opportunity. It's a call to think differently, to embrace the strange and the counterintuitive, and to push the boundaries of what we believe is possible. Who knows what breakthroughs might come from the minds of those who dare to ask the next big question? The story of entanglement isn't just about rewriting the rules of physics. It's about inspiring us to see the universe in a whole new light, one where the journey of discovery is as important as the answers we seek. And that, perhaps, is the greatest gift of this cosmic puzzle, the endless invitation to keep exploring. What if the very act of looking at the universe changes it? This isn't just a philosophical musing. It's a cornerstone of quantum mechanics, and it's especially vivid in the strange world of entanglement. When we measure entangled particles, something remarkable happens: their superposition. The fuzzy, undefined state where they exist as all possible outcomes at once collapses into a single, definite state. It's as if the universe is holding its breath, waiting for us to observe it before deciding how to behave. This process, known as the collapse of the wave function, has profound implications not just for physics, but for how we understand reality itself. To see how this works, let's revisit the concept of superposition. In the quantum realm, particles don't have definite properties until they're measured. Instead, they exist in a kind of blurred state where all possible outcomes coexist. Think of it like a spinning coin. It's neither heads nor tails until it lands. But when you measure an entangled particle, its superposition collapses and it chooses a specific state. Here's the twist: because the particles are entangled, this collapse isn't isolated. The moment you measure one particle, its entangled partner instantly snaps into a corresponding state, no matter how far apart they are. It's as if the act of observation ripples across the universe, linking the particles in a way that defies classical logic. This raises a fascinating question. What role does the observer play in shaping reality? In the classical world, we tend to think of observation as a passive act. We're simply recording what's already there. But in the quantum world, observation is anything but passive. It's an active process that forces particles to make up their minds, collapsing their possibilities into a single outcome. This idea has sparked intense debate among physicists and philosophers alike. Does the universe require an observer to define itself? Or is there something deeper going on, a hidden mechanism that determines the outcome of measurements without needing conscious intervention? One of the most famous thought experiments to explore this idea is Schrödinger's cat. In this scenario, a cat in a box is both alive and dead until someone opens the box and observes it. While this is a simplified analogy, it captures the essence of the observer's role in quantum mechanics. The act of measurement seems to crystallize reality from a sea of possibilities. But does this mean that consciousness itself is somehow fundamental to the universe? Some interpretations of quantum mechanics, like the Copenhagen interpretation, suggest that observation is key to collapsing the wave function. Others, like the many worlds interpretation, argue that every possible outcome actually happens, creating a branching multiverse where every measurement spawns a new reality. The implications of this are staggering. If observation plays such a central role in quantum mechanics, it blurs the line between science and philosophy, forcing us to rethink the nature of reality itself. Are we, as observers, active participants in shaping the universe, or are we simply uncovering a reality that exists independently of us? These questions don't just challenge our understanding of physics, they touch on the very essence of existence, inviting us to consider whether the universe is a fixed, objective reality or something more fluid and subjective. This debate isn't just theoretical, it's at the heart of some of the most cutting-edge experiments in quantum physics. Researchers are testing the limits of observation, exploring how different types of measurements affect entangled particles and whether the act of observation itself can be manipulated. These experiments are pushing the boundaries of what we know, revealing new layers of complexity in the quantum world. And with each discovery, we're reminded that the universe is far stranger and more interconnected than we ever imagined. So, what does this mean for our understanding of reality? If observation is so intimately tied to the behavior of entangled particles, it suggests that the universe is more dynamic and responsive than we once thought. It's as if the cosmos is in constant dialogue with itself, with every act of observation shaping the story of existence. This idea doesn't just rewrite the rules of physics, it invites us to see ourselves as part of a larger, more mysterious whole, where the boundaries between observer and observed are far blurrier than we ever realized. And as we continue to explore these ideas, we're not just uncovering the secrets of the quantum world, we're redefining what it means to exist within it. Now let's dive into a phenomenon that feels like it's pulled straight from a paradox, the quantum Zeno effect. Named after the ancient Greek philosopher Zeno, who famously argued that motion is an illusion, this effect reveals something equally counterintuitive in the quantum world. The act of watching something can actually stop it from changing. Imagine you're boiling a pot of water, but every time you glance at it, the water freezes in place, refusing to boil no matter how long you wait. It's a quirky analogy, but it captures the essence of the quantum Zeno effect, where observation doesn't just reveal reality, it actively shapes it. In the quantum realm, particles exist in a state of superposition, meaning they can be in multiple states at once until they're measured. But here's the twist: if you observe a quantum system frequently enough, you can effectively freeze it in place, preventing it from evolving or changing. This happens because each measurement collapses the system's wave function, resetting its state and halting its natural progression. It's like constantly interrupting a spinning top, keeping it from falling over. And when entanglement enters the picture, things get even more fascinating. Entangled particles linked across space and time can also be influenced by this effect. If you repeatedly measure one particle in an entangled pair, you can stabilize the entire system, preventing both particles from evolving independently. The quantum Zeno effect isn't just a theoretical curiosity, it has profound implications for the stability of quantum systems. In quantum computing, for example, maintaining the coherence of qubits, the building blocks of quantum information, is a major challenge. Qubits are notoriously fragile, easily disrupted by their environment. But by leveraging the quantum Zeno effect, scientists can freeze qubits in their desired states, protecting them from decoherence and improving their reliability. It's like giving quantum computers a pause button, allowing them to hold onto information long enough to perform complex calculations. But the applications don't stop there. The quantum Zeno effect could also play a role in developing ultra-secure communication systems. Imagine a network where entangled particles are constantly monitored, their states stabilized through frequent observations. This could create a quantum communication channel that's not only instantaneous but also incredibly resistant to interference. It's a glimpse into a future where the strange rules of quantum mechanics aren't just understood, they're harnessed to transform technology in ways we're only beginning to imagine. This interplay between observation, entanglement, and stability is a reminder of how deeply intertwined the quantum world is. It's not just a realm of particles and probabilities. It's a dynamic system where the act of looking can change the very fabric of reality. As we explore these ideas, we're not just uncovering the secrets of quantum mechanics, we're discovering tools that could reshape the future of technology. The quantum Zeno effect is more than a paradox. It's a doorway to a new understanding of how the universe works and how we might one day work with it. What if the way we think about information, its storage, its transfer, its very essence, is fundamentally incomplete? Quantum entanglement doesn't just challenge our understanding of particles and space, it's also rewriting the rules of information itself. In the classical world, information is straightforward. It's stored in bits, transferred through signals, and processed by algorithms. But in the quantum realm, information takes on a whole new dimension. It becomes fluid, dynamic, and deeply interconnected, defying the neat categories we've built to describe it. This is the world of quantum information, a place where entanglement isn't just a curiosity, it's the foundation of a revolutionary way to handle data. Let's start with the basics. In classical computing, information is stored in bits, which can be either a 0 or a 1. These bits are like tiny switches, flipping between two states to encode data. But quantum information operates on an entirely different level. Instead of bits, quantum systems use qubits, which can exist in a superposition of both 0 and 1 simultaneously. This means a single qubit can hold more information than a classical bit, but that's just the beginning. When qubits become entangled, their states become linked, creating correlations that allow them to store and process information in ways that classical systems simply can't match. It's like comparing a single note played on a piano to an entire symphony. Quantum information is richer, more complex, and capable of far greater depth. One of the most striking features of quantum information is its ability to be shared and manipulated in ways that seem almost magical. Take, for example, the concept of quantum teleportation. No, we're not talking about Star Trek-style transporters. Quantum teleportation is a process that allows the state of one qubit to be transferred to another, even if they're separated by vast distances. This isn't about moving matter, it's about moving information. By leveraging entanglement, scientists can teleport quantum information from one place to another without physically transmitting it through space. It's a process that's already been demonstrated in labs, and it has the potential to revolutionize how we think about communication and data transfer. But what makes quantum information truly game-changing is its potential for parallel processing. In a classical computer, operations are performed sequentially, one after another. But a quantum computer, with its entangled qubits, can explore multiple possibilities simultaneously. Imagine solving a maze not by trying one path at a time, but by exploring every possible route all at once. This ability to process vast amounts of information in parallel is what gives quantum computing its incredible power, making it uniquely suited for tackling complex problems like optimizing large systems, simulating molecular interactions, or cracking cryptographic codes. Of course, harnessing this potential isn't without its challenges. Quantum information is incredibly delicate, easily disrupted by its environment, a phenomenon known as decoherence. Scientists are working on ways to protect quantum states, using techniques like error correction and quantum error detection to keep qubits stable. These advancements are crucial for building practical quantum computers and networks, and they're already showing promise in labs around the world. The implications of quantum information go far beyond computing. In fields like cryptography, quantum entanglement offers the potential for unbreakable encryption. By encoding information in entangled particles, we can create communication channels that are inherently secure, as any attempt to intercept the data would immediately alter the quantum state, alerting the sender and rendering the information useless. It's a level of security that's impossible with classical systems, and it could transform everything from online banking to national defense. As we continue to explore the nature of quantum information, we're not just developing new technologies, we're redefining what information itself means. In a world where data can be stored in superpositions, transferred through entanglement and processed in parallel, the lines between the physical and the informational blur. It's a reminder that the universe is far more interconnected and dynamic than we once thought, and that the way we handle information, on both a practical and philosophical level, is poised for a seismic shift. The quantum revolution isn't just about faster computers or better encryption. It's about unlocking a new way of thinking about reality itself. And with each discovery, we're one step closer to a future where the boundaries of information are limited only by the imagination. Imagine watching a magician perform a trick so baffling that even the most seasoned skeptics are left scratching their heads. Now, picture that same level of mystery playing out on the quantum stage, where particles defy logic and measurements create more questions than answers. This is the heart of the quantum measurement problem, a puzzle so profound that it challenges not only our understanding of physics, but also the very nature of reality itself. And at the center of this enigma lies quantum entanglement, a phenomenon that turns every measurement into a cosmic sleight of hand. Let's break it down. In the classical world, measuring something is straightforward. You look at a thermometer and it tells you the temperature. You step on a scale and it gives you your weight. But in the quantum realm, measurement is anything but simple. Particles exist in a state of superposition, meaning they can be in multiple states at once, like a coin spinning in midair, neither heads nor tails until it lands. The moment you measure a particle, its superposition collapses and it chooses a single state. But here's the twist: when particles are entangled, measuring one instantly determines the state of its partner, no matter how far apart they are. It's as if the universe is performing a magic trick, where the act of looking at one coin forces the other to land on a specific side, even if it's light years away. This raises a perplexing question. What exactly happens during a quantum measurement? Does the act of observation somehow force particles to make up their minds? Or is there a deeper mechanism at play, one that we haven't yet uncovered? The answers aren't clear, and that's where the quantum measurement problem comes in. It's a debate that has divided physicists for decades, with some arguing that consciousness itself plays a role in collapsing the wave function, while others propose that hidden variables or alternative interpretations might explain the phenomenon. What's certain is that entanglement complicates the picture, creating a web of connections that defies our classical intuition. Think of entanglement as the magician's assistant, working behind the scenes to make the impossible seem effortless. When two particles are entangled, their properties are deeply intertwined, creating correlations that seem to transcend space and time. But when you measure one particle, it's as if the magician pulls back the curtain, revealing a reality that's both astonishing and deeply mysterious. The entanglement ensures that the measurement of one particle instantly affects the other, creating a paradox that challenges our understanding of cause and effect. It's like pulling a rabbit out of a hat, only to find that the rabbit was always there, and yet somehow it wasn't. This paradox isn't just a theoretical curiosity, it has real-world implications for how we interpret quantum mechanics. The famous Schrödinger's cat thought experiment, for example, hinges on the idea that a quantum system remains in superposition until it's observed. But with entanglement, the act of observation becomes even more complex. If entangled particles are part of a larger system, does observing one particle collapse the entire system's wave function? Or does the entanglement create a kind of quantum domino effect where each measurement ripples through the network of connected particles? These questions don't just challenge our understanding of measurement, they force us to rethink the very nature of reality. So, where does this leave us? The quantum measurement problem is far from solved, but it's also one of the most fertile grounds for new discoveries. As scientists continue to probe the mysteries of entanglement and measurement, they're uncovering insights that could reshape our understanding of the universe. From the possibility of hidden dimensions to the idea that reality itself might be observer-dependent, the implications are as profound as they are thrilling. And while the answers remain elusive, the journey to uncover them is a reminder that the universe is far stranger and more interconnected than we ever imagined. The magic of quantum mechanics isn't just in the tricks, it's in the endless questions that keep us searching for the truth. What if the universe's deepest secrets are hidden not in chaos but in perfect balance? This is the intriguing idea at the heart of symmetry, a fundamental principle that shapes everything from the tiniest particles to the vast cosmos. And when it comes to quantum entanglement, symmetry plays a starring role, acting as the invisible glue that binds particles together in ways that defy our everyday intuition. To understand how this works, let's take a closer look at the relationship between symmetry and entanglement, and how breaking that symmetry can unravel the delicate connections that make quantum mechanics so astonishing. Imagine a perfectly balanced scale with two identical weights resting on either side. No matter how you tilt the scale, the weights remain in harmony, their positions mirroring each other in perfect symmetry. In the quantum world, entangled particles are like those weights, their properties linked in a way that reflects this same balance. When two particles become entangled, their states are correlated: spin, position, momentum, creating a symmetry that transcends distance. It's as if the universe is saying, these particles are two sides of the same coin, forever connected by an invisible thread of symmetry. But what happens when that symmetry is broken? Picture the scale again, but this time one side is slightly heavier. The balance is disrupted and the harmony is lost. In the quantum realm, breaking symmetry can have a similar effect, disrupting the delicate connections between entangled particles. For example, introducing an external force like a magnetic field can alter the properties of one particle, causing its entangled partner to respond in a way that no longer mirrors its original state. The symmetry is broken and the entanglement is disrupted. It's a reminder that the quantum world is deeply sensitive to its environment, where even the smallest changes can have profound effects. This interplay between symmetry and entanglement isn't just a theoretical curiosity, it's a clue to the universe's underlying order. Symmetry is one of the most powerful tools in physics, helping us uncover patterns and principles that govern the behavior of particles and forces. From the elegant equations of quantum mechanics to the grand structure of spacetime, symmetry is the thread that weaves together the fabric of reality. And when we explore how symmetry enables entanglement, we're not just studying particles, we're glimpsing the hidden architecture of the cosmos. Take, for example, the concept of conservation laws, which are deeply tied to symmetry. In physics, certain quantities like energy or momentum are conserved, meaning they remain constant over time. These conservation laws arise from symmetries in the laws of nature, a principle known as Noether's theorem. In the context of entanglement, these symmetries ensure that the correlations between particles remain intact, even as they evolve over time. It's like a cosmic dance where the steps are choreographed by the underlying symmetries of the universe. And when those symmetries are respected, entanglement thrives, creating connections that seem almost magical. But what happens when we push these symmetries to their limits? What can breaking symmetry teach us about the nature of entanglement and the universe itself? These are questions that scientists are actively exploring, using experiments to probe how entanglement responds to changes in symmetry. By studying these effects, researchers are uncovering new insights into how quantum systems behave and how they might be harnessed for technologies like quantum computing and secure communication. It's a journey that takes us from the abstract world of symmetry to the cutting edge of practical science, showing how the most fundamental principles can have real-world applications. So, what does this mean for our understanding of the universe? If symmetry is the key to entanglement, it suggests that the cosmos is built on a foundation of balance and harmony, a hidden order that underlies the apparent chaos of the quantum world. And as we continue to explore this idea, we're not just uncovering the secrets of particles, we're discovering a deeper truth about the nature of reality itself. The story of symmetry and entanglement isn't just a chapter in physics, it's a window into the universe's most profound mysteries, inviting us to see the world in a whole new light. And with each discovery, we're reminded that the universe is far more elegant, interconnected, and beautiful than we ever imagined. Let's take a step back and consider the boundary between two worlds, one governed by the bizarre rules of quantum mechanics and the other by the familiar laws of classical physics. This boundary isn't just a line on a map, it's a dynamic frontier where the strange and the ordinary collide, creating phenomena that challenge our understanding of reality. At the heart of this collision lies quantum entanglement, a phenomenon that doesn't just defy classical intuition. It actively blurs the line between the quantum and classical realms, acting like a bridge that connects these two seemingly separate worlds. Picture a vast canyon with the quantum world on one side and the classical world on the other. On the quantum side, particles exist in superpositions, entangled states, and other mind-bending conditions that seem to defy logic. On the classical side, objects behave predictably, following the straightforward rules we've come to expect from everyday experience. Now imagine a bridge spanning this canyon, allowing particles to move between these two worlds. This bridge is entanglement, a phenomenon that doesn't just link particles across space, but also connects the quantum and classical domains, creating a seamless transition between the two. But how does this bridge work? In the quantum realm, particles can exist in multiple states at once, like a coin spinning in midair, neither heads nor tails until it's observed. When these particles become entangled, their states become linked, creating correlations that persist even when they're separated by vast distances. Yet, as these entangled particles interact with their environment, whether through collisions, measurements, or other interactions, they begin to lose their quantum properties, transitioning into the classical world. It's as if the bridge between the quantum and classical realms is constantly being crossed, with particles moving back and forth, influenced by the rules of both worlds. This transition isn't just a theoretical curiosity, it's a key part of understanding how the quantum world gives rise to the classical one. In the early universe, for example, everything was governed by quantum mechanics. But as the universe expanded and cooled, the quantum behavior of particles gave way to the classical behavior we see today. Entanglement played a crucial role in this transition, acting as the bridge that allowed the quantum and classical worlds to coexist and evolve together. It's a process that's still happening all around us, from the behavior of electrons in a lab to the way light interacts with matter in the world we experience every day. One of the most fascinating aspects of this bridge is how it challenges our intuition. In the classical world, objects have definite properties. A ball is either in your hand or on the ground, not both. But in the quantum world, particles can exist in multiple states at once. and entanglement creates connections that seem to ignore the boundaries of space and time. This blurring of the line between quantum and classical behavior forces us to rethink what we know about reality. It's as if the universe is telling us that the boundary between these two worlds isn't as sharp as we once thought, that there's a fluid, dynamic interaction between the strange and the familiar. This idea has profound implications for our understanding of the universe. If entanglement is the bridge between the quantum and classical realms, it could help us solve one of the biggest mysteries in physics: how the quantum world transitions into the classical one. This transition, known as the quantum to classical boundary, has puzzled scientists for decades. How do particles lose their quantum properties and become classical objects? Entanglement might hold the key, offering a framework where the quantum and classical worlds are not separate but deeply interconnected, with entanglement acting as the mechanism that facilitates their interaction. As we continue to explore this boundary, we're reminded that the universe is far more interconnected and dynamic than we ever imagined. The quantum classical boundary isn't just a line, it's a living, breathing frontier, constantly shifting and evolving as particles move between these two worlds. And with each discovery, we're not just uncovering the secrets of the quantum realm, we're gaining a deeper understanding of how the universe itself works. The bridge of entanglement isn't just a connection, it's a window into a reality that's more fluid, more mysterious, and more beautiful than we ever dreamed. And as we cross that bridge, we're not just exploring the universe, we're redefining what it means to understand it. What if the key to exploring the stars lies not in rocket fuel or advanced propulsion systems, but in the invisible threads of quantum entanglement? As humanity dreams of venturing deeper into the cosmos, this bizarre phenomenon could revolutionize the way we navigate and communicate across vast interstellar distances. Imagine a future where spacecraft don't rely on fragile radio signals or slow-moving probes. They use entanglement to send instantaneous messages and pinpoint their location with cosmic precision. It's a vision that sounds like science fiction, but it's rooted in the very real science of quantum mechanics. At the heart of this idea is the concept of entanglement-based communication. Today, when we send messages into space, we're limited by the speed of light. A signal from Mars to Earth takes anywhere from 4 to 24 minutes, depending on the planet's positions. For missions to distant stars, this delay becomes a major hurdle. But entangled particles don't play by these rules. When two particles are entangled, measuring one instantly determines the state of the other, no matter how far apart they are. This instantaneous connection could form the backbone of a quantum communication network, allowing spacecraft to send and receive data across the galaxy in real time. It's like having a cosmic telephone line where the conversation happens as if the two parties are standing side by side, even if they're separated by light years. But communication is only part of the picture. Quantum entanglement could also transform how we navigate the cosmos. Think of it as a cosmic GPS, but one that doesn't rely on satellites orbiting Earth. Instead, entangled particles could act as beacons, creating a network of quantum reference points across the universe. By measuring the entangled states of these particles, a spacecraft could determine its exact position relative to these beacons, even in the vast emptiness of interstellar space. It's a system that wouldn't just be faster and more accurate, it would be immune to the interference and signal degradation that plague traditional navigation methods. Imagine a spaceship charting its course through the galaxy with the precision of a laser beam, guided by the invisible hand of entanglement. This technology could open up entirely new possibilities for space exploration. Missions to distant stars, once thought to be the stuff of dreams, could become achievable realities. A quantum navigation system would allow probes to travel farther and faster, knowing exactly where they are at all times. And with entanglement-based communication, scientists on Earth could receive data from these missions instantaneously, enabling real-time decision-making and problem-solving. It's a future where the vastness of space becomes a little less daunting and the stars feel a little closer. Of course, there are challenges to overcome. Entangled particles are incredibly delicate, and maintaining their fragile states over interstellar distances would require groundbreaking advancements in technology. But the progress we've made so far is already remarkable. From quantum satellites like China's MISSIOS to experiments demonstrating entanglement over hundreds of kilometers, the building blocks of this cosmic network are falling into place. As we continue to refine these technologies, the dream of entanglement-powered space exploration is inching closer to reality. What's truly exciting is how this could redefine our relationship with the cosmos. Quantum entanglement isn't just a tool for exploration, it's a reminder that the universe is far more interconnected than we ever imagined. The same phenomenon that links particles across vast distances could one day link humanity to the stars, creating a bridge between Earth and the farthest reaches of the galaxy. And as we take those first steps into this quantum-powered future, we're not just exploring space, we're redefining what it means to venture into the unknown. The stars are calling, and entanglement might just be the key to answering that call. What if the ultimate goal of physics, a single, unified theory that explains everything, has been hiding in plain sight all along? Quantum entanglement, with its strange and profound connections, might just be the missing puzzle piece that finally brings together the two greatest theories of modern physics, quantum mechanics and general relativity. These two frameworks have long stood as the pillars of our understanding: quantum mechanics governing the tiny world of particles, and general relativity describing the vast cosmos. But they've always seemed incompatible, like two different languages trying to tell the same story. Now, entanglement is emerging as the bridge that could unite them, offering a glimpse into a deeper, more unified reality. Think of the quest for a unified theory as trying to solve a cosmic jigsaw puzzle. On one side, you have quantum mechanics with its bizarre rules of superposition, entanglement, and uncertainty. On the other, you have general relativity, which paints a smooth, geometric picture of spacetime warped by gravity. The problem: the pieces don't quite fit. Quantum mechanics thrives on probabilities and discrete jumps, while general relativity is all about smooth curves and deterministic laws. It's like trying to combine a digital photograph with a painting. They're both images, but the way they're built is fundamentally different. That's where entanglement comes in. This phenomenon, which links particles across vast distances, might hold the key to connecting these two worlds, revealing a hidden layer of reality where both theories can coexist. One of the most promising ideas in this quest is quantum gravity, a theoretical framework that seeks to describe gravity using the principles of quantum mechanics. At its core, quantum gravity suggests that spacetime itself might be made up of tiny, discrete units like pixels on a screen, rather than being smooth and continuous. An entanglement could be the glue that holds these pixels together, creating the fabric of spacetime from the bottom up. It's as if the universe is a vast, interconnected network, with entanglement weaving the threads that bind everything from the smallest particles to the largest galaxies. But how does this work in practice? Imagine spacetime as a tapestry, with each thread representing an entangled connection between particles. The strength and pattern of these threads determine the shape and behavior of spacetime itself. In this view, gravity isn't just a force, it's an emergent property, something that arises from the intricate web of entangled connections. This idea, known as spacetime entanglement, offers a radical new way to think about the universe, where the fabric of reality is stitched together by the quantum interactions of its smallest components. The implications of this are staggering. if entanglement truly bridges the gap between quantum mechanics and general relativity, it could solve some of the deepest mysteries in physics. For example, it might explain what happens inside black holes, where the rules of quantum mechanics and gravity collide in spectacular fashion. Or it could shed light on the Big Bang, revealing how the universe emerged from a quantum state into the classical world we see today. These aren't just abstract questions, they're the keys to understanding the very nature of existence. Of course, this is still a work in progress. The idea of spacetime entanglement is both thrilling and speculative, a frontier of physics that's being explored through advanced theories and experiments. But the progress so far is encouraging. From the holographic principle to string theory, researchers are uncovering new ways to connect the quantum and cosmic realms, with entanglement at the heart of these discoveries. It's a reminder that the universe is far more interconnected and mysterious than we ever imagined, and that the answers to our deepest questions might lie in the most unexpected places. As we continue to explore these ideas, we're not just solving a scientific puzzle, we're uncovering a new way to see reality. The quest for a unified theory isn't just about finding the right equations, it's about discovering the hidden connections that make the universe work. And with entanglement as our guide, we're one step closer to unraveling the universe's deepest secrets. The journey is far from over, but the possibilities are as vast and thrilling as the cosmos itself. As we wrap up this journey through the strange and wondrous world of quantum entanglement, one thing is clear: this phenomenon is far more than a scientific curiosity. It's a revolution in how we understand the universe. From the smallest particles to the vast expanse of space and time, entanglement is rewriting the rules, challenging everything we thought we knew about reality. It's as if the cosmos has handed us a new set of keys, unlocking doors to realms we once believed were beyond our reach. At its heart, entanglement reveals a universe that's deeply interconnected, where particles separated by light years can instantly influence each other, defying the limits of space and time. This isn't just a quirk of physics, it's a profound insight into the fabric of existence. We've seen how entanglement challenges Einstein's theory of relativity, blurs the line between the quantum and classical worlds, and even offers tantalizing clues about the nature of black holes and the Big Bang. It's a reminder that the universe is far stranger and more beautiful than we ever imagined. But the implications of entanglement go beyond theory. This phenomenon is already reshaping technology, from quantum computing to secure communication, and it's opening up new possibilities for space exploration and even the search for extraterrestrial life. Imagine a future where we harness the power of entanglement to build faster, more secure systems, or to navigate the cosmos with unprecedented precision. The potential is limitless, and we're only just beginning to scratch the surface. What's truly remarkable is how entanglement forces us to rethink not just science, but our place in the universe. If particles can be so deeply connected, what does that say about us? Are we, too, part of a larger, more intricate web, bound together by invisible threads that transcend space and time? It's a humbling thought, one that invites us to see ourselves not as isolated beings, but as part of a vast, interconnected whole. As we reflect on these ideas, let's end with a question that captures the essence of this journey. What if the universe is not a collection of separate objects, but a single, unified tapestry woven together by the threads of entanglement? What would that mean for how we see ourselves, our world, and our future? The answers are still out there, waiting to be discovered, and the adventure is just beginning. Thank you for joining me on this exploration of quantum entanglement and its profound implications. If this video sparked your curiosity, don't stop here. Dive deeper into the comments and share your thoughts. What aspect of entanglement fascinates you the most? How do you think it will shape the future of science and technology? Let's keep the conversation going. And if you enjoyed this journey, be sure to subscribe for more mind-expanding content. Until next time, keep questioning, keep exploring, and remember, the universe is far more mysterious and interconnected than we ever dreamed. See you in the next